Good morning everyone, I'm Forough from Imperial College London, and today I will be presenting our work, Dynamic Probabilistic Noise Injection for Membership Inference Defense, or DynaNoise. Why membership inference matters? Machine learning models are trained on increasingly sensitive data, and they memorize more than we would like. So membership inference attacks exploit exactly this. As the diagram shows, the attacker submits a query to the target model, observes its output, and feeds it to an attack classifier that answers one simple but dangerous question. Was this sample in the training set? Why does one bit of information matter? Imagine a hospital deploys a diagnostic model. If an attacker learns that a patient's record was in the training data, they have learned that the person visited the hospital. In finance, for example, membership can expose a client's investment history, so membership alone is a real privacy violation. The classical defense is differential privacy. Add noise either during training like DPSGD or at inference, but these defenses inject a fixed amount of noise for every query, and that creates a rigid trade-offs. If noise is small, modern attacks, especially likelihood ratio attacks like Lyra, still succeed. If the noise is large, model accuracy collapses. So our key observation is that queries are not equally risky. A confident, peaked prediction leaks far more membership signals than an uncertain one. So uniform noise wastes utility on safe, queries and underprotects the dangerous ones. So why treat them all the same? Here is our threat model briefly. So the adversary has black box access. They can query the model and observe the full probability vector in a standard, machine learning as a service setting. Their goal is to distinguish members from non-members, and we assume a limited query regime, so repeated identical queries are rate limited or logged, which is common in deployed systems. And to be upfront about the scope, DynaNoise targets scope-based attacks. Label-only attacks are outside this work. DynaNoise is a purely post-hoc inference time defense, so no retraining, no ensembles, no architectural changes are required. You can drop it on top of a pre-trained AlexNet or Decilbert today, as shown in the pipeline here. It has, three stages. First, we analyze the sensitivity of each incoming query using the model's output distribution. Second, we inject, Gaussian noise whose variance is scaled at that risk. Third, we apply a probabilistic smoothing step to renormalize the outputs. The whole mechanism has just three interpretable hyperparameters: the base variance, a scaling, factor, and the temperature. But how does DynaNoise work? Concretely, for each query, we compute the Shannon entropy of the softmax output and define the sensitivity score R of Q as 1 minus the normalized entropy, so it leaves between 0 and 1. A confident low entropy prediction, exactly the kind that screams training sample, gets a score near to 1. We then scale the noise variance linearly with that score. Sigma squared of Q equals the base variance times 1 plus lambda times R of Q. We add Gaussian noise with that variance to the raw logits, and finally renormalize with a temperature scale softmax, which smoothes the distribution while preserving the predicted label ordering. And the cost per query is a single noise draw and a single softmax. linear in number of classes, and it is essentially free. Evaluating defenses is itself, tricky. Papers usually show Pareto curves, which are informative but hard to compare across settings. So we propose a simple scalar called midput, the membership inference defense privacy utility trade-off. So for each attack, midput is the reduction in attack success rate minus the accuracy drop the defense causes. We report it per attack plus an overall score averaged across all 6 attacks. Values near 1 mean a strong privacy gain at little utility cost. Negative values means the defense hurt accuracy more than it helped privacy. And one important point is that it's a summary measure. It complements per attack results and Pareto analysis. It doesn't replace them. And we report all raw attack success rates alongside it in the paper actually. Here is the our evaluation setup and key results. So we evaluated on 3 benchmarks spanning vision and language, CFAR10 and ImageNet 10 with AlexNet, and SST2 with Decilbert against 6 attacks covering every major family, including Lyra, the strongest known attack, and 5 state-of-the-art defenses. So DynaNoise, through our experiments, achieves the best overall privacy utility trade-off on both vision benchmarks. Attacks drop to essentially coin flip accuracy. For example, the shadow attack falls from 64% to 50%, while the model loses less than a single point of accuracy. The instructive contrast is HAMP. It also drives attacks to chance, but by suppressing confidence uniformly on every query, it pays with up to 14 points of accuracy on vision models. On SST2, where Decilbert is already well calibrated and leakage is weak, global smoothing works fine and HAMP edges us out slightly. But DynaNoise remains a close second with essentially zero accuracy loss. The pattern across all 3 datasets is the same. Adapt protection to risk and you get privacy without paying the utility tax. So far you have seen attack numbers. Now let me show you what DynaNoise actually does to the model's output. These are percentile plots, maximum confidence on top, predictive entropy below. Blue is training members, orange is non-members. Look at the before plots on the left. Members reach high confidence and low entropy at much earlier percentiles than non-members. That gap between the blue and orange curves is the membership signal. Every attack we evaluated, from simple thresholding to Lyra, ultimately exploits this gap. Now the after plots. The curves converge across the percentile range. The member confidence spike is suppressed and the entropy distributions align. The signal the attacker needs is gone. That's exactly why attack success collapses to near chance. And note what did not happen. The distributions weren't flattered to uniform. The prediction ranking is preserved, and that's why accuracy stays as baseline. So it closes the gap and doesn't destroy the output. Now let's talk about the overhead. So efficiency is where DynaNoise really separates itself. Per sample inference latency is 0.143 milliseconds versus 0.141 for the undefended model, about 1% overhead. HAMP doubles inference time because of its extra forward pass, and memguard, which solves an optimization problem for every single query, is nearly 200 times slower. And unlike adversarial regularization, relaxed loss, or Selena, we require no retraining at all. Selena alone costs over 2.5 times the baseline training. Dynanoise is the lightest defense in this comparison by a wide margin, which makes it immediately deployable on pre-trained models. Now let's discuss the limitations and conclude the presentation. So to be transparent about limitations, I need to say that Dynanoise is an empirical defense. We don't provide formal differential privacy bounds, and deriving them from or for entropy adaptive perturbation is an open problem. Like all stochastic inference time defenses, repeated queries could average out the noise, so we assume rate limiting. Caching noisy responses is a practical mitigation. Label only attacks are out of scope, and as with every defense we compared against, some hyperparameter tuning helps. So to conclude, we presented Dynanoise, a post-hoc defense that scales noise to per query risk using entropy. It achieves the best privacy utility trade-off on vision benchmarks under 6 attacks, including Lyra, at 1% overhead and 0 retraining. We also propose midput, a modular scalar metric for comparing defenses. So the broader message is simple. Protection should adapt to risk, not be applied uniformly. Future work includes alternative sensitivity estimators and integrating adaptive noise with formal privacy techniques. Okay, so thank you very much for your attention. If you have any question, please don't hesitate to send me an email and we can discuss it.